Hello, good people. How are you? Welcome to Physical Science Revision for Term 3. Today I brought a question paper for grade 11. It was a question paper from the Eastern Cape Province, the Department of Education for OR Tambo Inland District. We are trying to cover as much ground as we can by bringing question papers from various districts and provinces so that you can get enough exposure for all your questions that you can actually get in your exam. So, good people, let's use this question paper as our revision guide. Whatsoever that we do here, it is to help us, to guide us in terms of preparing for our exams. So this question paper was a controlled test for September 2023. It was housing 100 marks and it was supposed to be written in what? In 2 hours. So you will see that our question paper is actually into multiple choice questions. So there is a section for multiple choice questions, and then there is a section that comes with structured and open-ended questions. So let's get started with our multiple choice questions. So I've got 8 questions that were multiple choice questions, which were out of 16 marks, and then the remaining ones were the ones which made a total of what? Of 100 marks. So on your multiple choice questions, you know that it's a norm that they give you A, B, C, or D, and there is always only one correct answer. So let's choose the most accurate answer. That becomes our final answer. Now they are saying a few drops of bromothiamine blue indicator are added to a hydrochloric acid. When ammonium hydroxide is added to this solution, the color of the indicator will change from to what? So we know that bromothiol blue is an acid-base indicator which changes color from blue to yellow in the presence of a what? In the presence of an acid. So since initially we had what? Hydrochloric acid being added, so each color, the color changed from blue to yellow. But when ammonium hydroxide was now added, it later actually what? Changed from yellow back to blue, because we know that if you actually get to react hydrochloric acid with what? With ammonium hydroxide, you are what? You are neutralizing. This is an acid base reaction, and we know that an acid base reaction is what? It's neutralization. So you are going back to the neutral solution, which would actually get to give you the what? The color for blue. Or else we would say that in the presence of a what? Of a base, your indicator becomes what? Becomes blue. So the color change was supposed to be from yellow to blue. So the answer there was supposed to be A. That was the answer there. Because initially we added an acid, so our color was yellow. And then when we added a base, our color now changed from what? From yellow to blue. Now we are now saying that the correct formula for ethanoic acid is what? So out of these ones, which one is ethanoic acid? We know that this one is nitric acid. So that one is in nitric acid. This one is sulfuric acid. And then this one is what we refer to as acetic acid or ethanoic acid. Ethanoic acid. Most people, they know it as acetic acid. And then when you are at home, this is what you refer to as what? Vinegar. And then this one, it's ammonia. So the correct answer there was supposed to be what? To be C. Now let's go to 1.3. So 1.3 was saying, which of the following graph does not illustrate the behavior of ideal gas? So under ideal gas, what is the behavior that is illustrated? So the first one, it's defined by Bohr's law. And then the second one is defined by what? By Chau's law. And what does Bohr's law say? Bohr's law says that pressure is directly proportional to 1 over V, or else pressure is directly proportional to the what? It's inversely proportional to your volume when your temperature is constant. So the graph for this would be something that is to say either pressure is there and volume is here, and then you'll be having something like this, or else you have your volume and then your pressure and you have something like this, or else you have your pressure here and then you have got your 1 over V, and then this is where you would have your graph like that. That is for what? For Boyle's law. And Boyle's law obeys what? The ideal gas behavior. And then we can see that on our A, it is actually indicating what? Boyle's law. So this is out because it actually illustrates ideal gas behavior. And then if we go to B, this illustrates volume is directly proportional to temperature. And this is what our Chau's law says. It says that for a given fixed mass of gas, in an enclosed system at a constant pressure, our volume will vary directly proportional to temperature. So this is Chau's law. So this is out because it actually obeys what? Ideal gas behavior. And then here they are saying pressure times volume is a constant when pressure is changing. So this is to say PV is equal to a constant. And this is what this law, which is the Boyle's law, actually says. So this one also obeys ideal gas law. But when you go to D now, it is now saying 1 over P is constant when volume is changing. This is actually incorrect. So this does not illustrate the behavior of ideal gas. So our answer was supposed to be D. So our answer there was just supposed to be D. D does not illustrate the ideal gas behavior. It is actually illustrating something else, which is not the ideal gas behavior. How do you know the ideal gas behavior? Anything that obeys Boyle's law or Chau's law actually illustrate what? Ideal gas behavior. So anything outside that, it does not illustrate the ideal gas behavior. So our answer was 1.3. For 1.3 was going to be D. And then for 1.4, here we are saying that according to Boyle's law, which option is correct? According to Boyle's law, which option is correct here? Does pressure vary directly proportional to 1 over V? Yes. According to Boyle's law, it says pressure is directly proportional to 1 over V. And this is what this is saying. So this might be our answer, which is A. What about B? Volume is directly proportional to temperature. This is Chau's law. And then pressure is directly proportional to volume. This is incorrect. And then volume is actually directly proportional to 1 over T. This is incorrect. So our answer was going to be A for Boyle's law. 1.5, in a 20-gram sample of molecules, which sample below has the greatest number of moles? So here we need to calculate the number of moles of each individual sample to actually get to compare which one has got the greatest number there. So the number of moles of ammonia, which is NH3, we know that the number of moles, you calculate the number of moles by saying that number of moles is equal to what? To mass over, it's equal to mass over the molecular mass. So we need to calculate the number of moles of ammonia given a 20-gram sample. You divide by the molecular mass of ammonia, which is 4. In atomic mass for nitrogen, it's 14. Atomic mass for hydrogen, it's 1. So here it's 14 plus 1 times 3. So this one will be equal to 17. So divide by 17 grams per each mole of what? Per each mole of ammonia. This was going to give me what? This was going to give me 1.2 moles. And then the number of moles for nitrogen, given a 20-gram sample, I would divide by the molecular mass of that. That is just 2 times 14. This would be equal to 28. So this was going to be 28 gram per mole. And then the number of moles there was just going to be equal to 0.7. And then for carbon dioxide, it's number of moles for carbon dioxide would be equal to 20 grams divided by the molar mass there would be 12 plus 16 times 2. This is equivalent to 44. So you'd come and divide by 44 grams per mole. So this one would be per mole. And then here the answer 20 divided by 44, it was going to be 0.45 moles. And then you go to the number of moles of what? Of hydrogen. This was going to be equal to 20 grams divided by 20 grams divided by this was going to be 2. So you divide by 2 there, it was going to give you 10 moles. So which one has got the greatest value there? You can see that 10 moles is greater than 1.2, which is greater than this one. So our nitrogen was going to, our hydrogen, sorry, was going to have the greatest number of what? Of moles. Now let's look at 1.5. Let's look at 1.5. Let's look at 1.5. So 1.5 was now saying that the chemical equation that represents an endothermic reaction is which one? How do we identify an endothermic reaction? For an endothermic reaction, we know that we would be having reactants, and these reactants, they need to absorb energy. And the energy absorbs, it's either in light, it's either as light or as what? As heat. And then you then get to form what? Your products. That is to say what? Our delta H would be greater than 0, where you have got the enthalpy of your products being greater than the enthalpy of your reactants. So we are looking for a reaction which either gives us this or that or else this. So let's look at our reactions. Reaction A, it's saying zinc plus hydrochloric acid, and then it forms zinc chloride plus hydrogen plus heat. So this one, it's exothermic because it is releasing heat. So this one is out. And then this one, ammonium nitrate plus water to form ammonium and nitrate. This actually what? It's endothermic because it shows that delta H is greater than what? Delta H is greater than 0. This means the enthalpy of your products will be greater than enthalpy of your reactants. So this is our answer. So for an endothermic reaction, this is what we are looking for. Others, you can see that here we have got a negative. This is exothermic. This is exothermic. So our answer was just going to be equal to what? It was just going to be equal to B. So the answer that you were supposed to actually get to choose there was B. That was the answer that you were supposed to choose. Now let's go to the following question. 1.7 says, 1.7 actually says that 0.5 mole sodium sulfate is dissolved in 500 cubic centimeters of water. The concentration of the sodium sulfate is. What is the concentration of the sodium sulfate? How do we find concentration? We say concentration is equal to number of moles divided by the volume. And this volume has to be in decimeter cubed. So you can see that your volume here was given in cubic centimeters. So you need to divide that volume by what? By 1000 cubic centimeters, because for 1 decimeter cubed we have got 1000 cubic centimeters. So by dividing, you are going to find your volume as 0.5 decimeter cubed. Now your moles, your number of moles is just 0.5, so you would say 0.5 moles divided by 0.5 decimeter cubed. Your answer was just supposed to be equal to what? So your answer there was just supposed to be equal to 1 mole per decimeter cubed. So the answer that you're looking for is C. That is 1 mole per decimeter cubed. Now 1.8, which is our final question for our multiple choice questions, it says the number of ions present in 2 moles, the number of ions present in 2 moles of what? Of copper chloride. So you can see that here you would be having Cu2 plus ions, and then you'll be having Cl minus. But these Cl minus, they are 2. So in each compound, which is just one compound, you would be having what? 3 ions. And then now, what about in 2 moles? So this is where we get to say that 1 mole actually represents how many ions. So you would know that your standard representation according to Avogadro's constant, we know that 1 mole of any compound represents is equal to 6.02 times 10 to the power 23 entities. And when we say entities, it's either atoms, which is your particles, or else it's either molecules, or else it's either what? Ions that can be found there. So now, if 1 mole is representing this, what about 2 moles? 2 moles would be equal to 2 times 6.02 times 10 to the power 23 ions. And then now we know that our compound, each compound has got 3 ions on each one. And then if it's now 2 moles of that compound, it will now be equal to what? 3 times 2 times 6.02 times 10 to the power 23 ions. So this one was actually going to give us what? It was actually going to give us 6 times what? 6.02 times 10 to the power 23. So our answer was just supposed to be C. Now let's go to the following question. Now, question number 2, we are given that the following reaction between ammonia and oxygen, they take place in a closed system at constant temperature and pressure. And then we get to know that this reaction is given the course of reaction to be like this. So let me just get to take it upwards so that we can see our questions. So now we are now saying that define the term activated complex. We know that an activated complex is going to be found here. And what is our activated complex? Let's say, for example, you have got your ammonia, which is to say it will be bonded like that. And then when you react with oxygen, which is bonded like that, you would need to actually get to break these bonds. You need to break these bonds, break that bond, so that at some point in time, you would now need to start forming the nitrogen oxygen bond. So before that nitrogen oxygen bond, you would actually be having something like this. You have actually broken that bond that was here. You are trying now to join this, but this also, you broken that bond. So this temporal transition, or else the unstable transition, this unstable transition state, this unstable transition state, uh, this temporal transition state from reactants to products is what we refer to as what? As the activated complex. So how were you going to define it, or else how were you going to write it as a statement? You were just supposed to actually come here and say, for 2.1, an activated complex is the unstable temporary state, the unstable temporary state, or else let me call it transition state, the unstable transition state from reactants to what? To products. So we are transitioning from reactants to products. So that temporary and unstable transition state is what we are referring to as an activated complex, or else you'd actually get to call the temporary unstable arrangements of what? Of reactant atoms before they start forming what? Your products. But this will be the simplest definition. Now let's look into the following question. It says, is the reaction exothermic or endothermic? Give a reason for the answer. So an exothermic reaction, we know that enthalpy of products will be less than enthalpy of reactants. So that our heat of reaction or else change in enthalpy will be less than zero, because we are saying that here we would actually get to what? To emit or release energy. So here would be releasing energy. But for endothermic, we need to absorb that energy. So how do you absorb energy? You need to actually get to say H of reactants plus that enthalpy energy, which is usually your activating energy, to actually get to form what? To actually get to form your enthalpy of products at some point in time. So your H reactants will be greater than your H products. That would be endothermic. So let's look onto our what? Onto our graph. Is it going to give us option A or option B? Then we can be able to determine if it's exothermic or endothermic. So you can see that the enthalpy of product of reactants here, they are greater than the enthalpy of your products. So this is actually what? Endothermic. Delta H is greater than zero here. So this is actually endothermic. So you are just going to actually come here and actually say that you are just going to come. Let me just get to erase this so that I can create space. You are just supposed to come and say for 2.2, you're going to say that the reaction is what? Endothermic. And the reason being H of your reactants is greater than H of your products. That was going to be your reason. You would actually get to say that because the enthalpy of your reactants, these ones are your reactants, is greater than the enthalpy of your what? Of your products. Is greater than the enthalpy of your products. Then you are done. Then now let's go to the following. Use the information on the graph and write down the value of the following. So you need the value of the activated complex. So the value of the activated complex becomes the peak value that you have on your graph. The peak value of your graph, that becomes your what? Your activation energy. That becomes your activated complex. And then the energy absorbed becomes the energy of your activation, which is actually given by the energy of the what? Of the activated complex minus the enthalpy of the what? Of the reactants. This is how you usually get to calculate the energy of absorbed or else your activated energy. Now, in heat of reaction is more like what? Enthalpy change, which is just given by enthalpy of products minus enthalpy of what? Of reactants. So this is what you're just supposed to come and do and then later give the values. So this is what we want to do using our graph that is given below. So we are doing 2.31 up to 2.33. So let me just get to wrap this so that I'll actually get to write my answers here. So I would say that for 2.31, where they were looking for the energy of the what? Of the activated complex. Energy of the activated complex, we say that it is equal to the peak. So our peak is here, and then the value corresponding to that, it's what? 2670 kilojoules. It's kilojoules per mole. That is the those are the units given there, kilojoules per mole. And then what about 2.32? 2.32, we're looking for the what? For the energy absorbed. We are looking for the energy absorbed. Energy absorbed is this difference here that you are seeing here. This activated energy, this difference here, to say that the activated complex minus the what? The reactants. So this was just going to be 2670 minus 400. And this was going to give us what? 2200 and what? 60. It was going to be 2270 there. So let me just get to write it neatly. 2670 minus 400 gives you 2270 kilojoules per what? Per mole. And then now you are looking for 2.33. They said heat of reaction. Heat of what? Heat of reaction. We know that our heat of reaction is just the change in enthalpy, which is enthalpy of products minus enthalpy of what? Reactants. What is the enthalpy of our products? It's 400 minus enthalpy of our reactants is just 183.3. Now, what becomes our answer? Let me just get to erase below there. Our answer would now be equal to, if you say 400 minus 183.3, that will give you an answer of negative, it was going to be negative 216.7. This was actually what? Kilojoules per mole. So that is how you would have calculated this. Now let's go to the following question. You would see that the following question is actually on the next page, but it has to do with this graph. It has to do with that graph. So they're saying now calculate the activation energy. They are saying calculate the activation energy for the reverse reaction. So since we know that for us to calculate activation energy, we usually get to say that activation energy is equal to the energy of your activated complex minus the enthalpy of reactants. Because now it's a reverse reaction, we will subtract the enthalpy of the products because the products they now become reactants. So that is what we are looking for on our graph. That is for what? That is for 2.34. Now let's go back to our graph and then let's check for that information. So this is the enthalpy of our activated complex, and then this is the enthalpy of our products, because now we are coming from these products going back, that is the reverse reaction. So these ones become reactants now because we are now going back as reverse. So we will take this one and that one, and then we can calculate our activation energy of what? Of our of our reverse reaction. So the activation energy of the reverse reaction becomes 2670 minus 183.3, and this should give you a value of what? That was going to give you a value of 2486.7 kilojoules per mole. That was the value for your activation energy on the reverse reaction. What about now? They're saying 2.4. Now a catalyst is added to the above reaction. Redraw the graph and show the effect of the addition of the catalyst. So what is the main job of a catalyst? We know that a catalyst initially, its main job is to actually get to lower the activation energy. Lower the activation energy of our reaction so that our reaction can actually get to speed up in terms of its pace. So we need to speed up the rate of reaction through lowering the activation energy. So what we want to lower is this one, because we know that our peak, this is where we have got our activated complex, and then from our reactants here. So these being our reactants, and then these ones being our activated complex. We said this one was 2770, this one was 400, and this was our energy there in kilojoules per mole. So you would have just came and said we need to lower the activation energy. So by lowering the activation energy, the course of reaction would actually go in this way. But you will see that you simply have the what? The same products at the end. You are simply having the same products at the end. So you would have just came and indicated this to say with catalyst. You can see that we have lowered the what? The activated complex value. Therefore, it simply means that our activation energy has actually been lowered as well. So this being our activation energy, it has actually been lowered. So that is what you were just supposed to draw there. Where here you have got what? Progress of what? Progress of time. So that is what you were just supposed to draw there. So now let's go to the following questions and hear what the following questions are saying. So now, question number 3. Now, question number 3. Just allow me to rub there. Question number 3. Question number 3 is now saying, consider the balanced equations for the reaction of water with nitric acid and ammonia below. And then they're saying, define a base in terms of the Lowry-Bromstead theory. So how do you define a base in terms of the Lowry-Bromstead theory? We know that Arrhenius say that if you are to actually get to dissolve or else to dissociate a substance in water and then it gets to form OH minus ions in water, that becomes a base. So any substance that adds OH minus in water, it's a base in terms of what? Of an Arrhenius theory. So now Lowry and Bromstead, they actually saw that this theorem was limited to what? To acids and bases in solution. What about those acids and bases that actually do not dissolve in water? That's when they came to say that you can actually get to define a base as a proton accept. So according to these guys, a base is actually a what? A proton accept. So maybe someone clever would just come and say, according to the Lowry Bronsted theory, a base is a proton accept. Anything that accepts protons, which are just H plus ions, anything that accepts H plus ions, it becomes a what? A base. And then now they're saying, write down the formula or name of ampholyte in the above reactions. What is an ampholyte? An ampholyte is a substance that can either act as an acid in another reaction or else act as a base in a different reaction. So we can see that here we have got nitric acid, it is a base. And then our water, it is an acid. Why? Because it is actually, so we can actually see, sorry, I interchanged there. Our nitric acid is actually our acid. And then this one is a base. From nitric acid, it's an acid. It is actually donating or else it is actually what? Giving protons. So our water accepted a proton there, which is an H plus. And then from H2, it went to what? To H3. So here our water is a base. But when you come here, this ammonia, we know that ammonia is a base. And then when it reacts with water, it actually receives H plus ions. So this one is an acid. So we can see that our water is acting as an ampholyte. It can either be a base or else an acid. So here you are just supposed to come and write what? H2O. Or else let me do this. So here you were just supposed to come and say the answer there was just supposed to be H2O, because they said write a formula or else a name. So a name would be water. That is the name of that. Now they are saying write down the formula of the two conjugate acid base pairs in reaction 2. Now allow me to just get to erase this so that I can explain. What is an acid base? What is an acid conjugate base pair? We know that according to Lowry-Bromstead theory, they say that every acid and every base, it has got its own conjugate acid or conjugate base. Like for example, this acid here, it has got its conjugate base here. This is an example. Why? Because here ammonia, it's actually a what? A base, because it receives protons to become nitric acid. If we are to actually go reverse, this would be receiving a proton. But if we are going forward, I'm saying that if we are to go reverse, if the reaction is going in the reverse, this is the one that is giving a proton. But if we are going forward, this is the one that is giving a proton. So this acid has got its own conjugate base. And then for reaction 2, ammonia here, it's a base. And then you can see that ammonium here becomes it becomes the conjugate acid. Why do we say that? Because here ammonia is receiving H from water. So if we are going forward, this is receiving. But when we are now coming backward, which is reverse, ammonium is the one that is giving the what? The H plus. So on our second reaction, the conjugate acid and base pairs there, we're just going to be, so this is actually for what? For 3.4. So for 3.4, you were just going to say that you were just going to take ammonia as the base, and then its conjugate base, its conjugate acid was going to be what? Ammonium. It was going to be ammonium. And then you can also get to take what? Water. That will be water. This one is an acid. And its conjugate base, would be what? It would be OH minus. Those were this one was the base and conjugate acid pair, acid and conjugate base pair. So that is what we were just supposed to write there, these two. And then let's go to our questions below. Let's get to see. They're now saying, is the solution in reaction 2 acidic or basic or alkaline? Give a reason for your answer. Now, what's happening here? What's happening here? This is a base and it's reacting with water. And we know that water sometimes it has got a pH of 7. We usually take water as having a pH of 7. And then definitely you would see that at the end of the day, you are forming what? An OH minus. So according to Arrhenius, if we are increasing the OH minus ions, we are in what? In alkaline solution. So you can see that we have increased the OH minus here. So this is alkaline because this one, it's a base. Ammonia, it's a base, it's a strong base. And then when you come to water, water is usually either treated as acidic or base because its pH, we usually take it from 6.0 to what? To 7.0. And we know that the neutral solution, or else let's get to say something that is neutral, it's something that is at a pH of 7. So the pH of water can either be, let me get to say that it can either be acidic, it can either be weak acidic or weak basic, but we usually get to take it as 7 to be neutral. So having a strong base and this weak acid, you are going to form a what? A basic solution. And also from this, you can actually get to see that we are increasing our what? Our OH minus. So at some point in time, you just come and say that this solution was what? Was basic. And what would be your reason there? You would come and say basic or else alkaline. Because of the presence of an OH minus. Someone would have said that we are reacting a weak acid with a what? With a strong base. So this one is a weak, very weak acid. It's a very weak. This one is a very weak acid with a strong base. So if you actually get to react a strong base with a very weak acid, you will form an what? An alkaline solution. But however, according to Arrhenius, once we have got OH minus ions being present, we know that it becomes an alkaline solution. Now they are saying calcium hydroxide reacts with nitric acid to produce the following product, an unknown Y. The equation for the reaction is calcium hydroxide plus nitric acid, and then it forms calcium nitrate plus Y. Now the question that comes is to say that write down the formula of Y if we are going to react our calcium hydroxide with what? Our calcium hydroxide, let me just get to erase that. I'm trying to erase. So at some point in time, we get to see that our calcium hydroxide is reacting with nitric acid. So this one is what? This one, it's a base, and then this one is an acid. So what happens if you react a base and an acid? You are going to have what we refer to as neutralization reaction. This one would be a neutralization reaction. And when you neutralize an acid with a base, you are going to form a salt. And after forming a salt, you also form water. So from our reaction, we have got our salt. So this is definitely water. So this one is what? It's water. Or else its formula would be H2O. Now they are saying write down a balanced equation for the dissolution of sulfuric acid. A balanced equation for the dissolution of sulfuric acid. How does sulfuric acid dissolve? How does sulfuric acid dissolve? How does sulfuric acid dissolve? Maybe I can just write it here. So the dissolution of sulfuric acid, this is our sulfuric acid. So when it dissolves in water, so dissolution, it's a reaction with water. So you react it with water, it gets to dissolve to form what? So maybe at some point in time, I was just supposed to find a big enough space to write that. So let me just get to write it this side. The equation would be to say that our sulfuric acid reacts with water to form what? It reacts with water. It forms sulfate ions. That is from this. And then we actually get to what? To donate these H plus ions to our water. So it will become H3O plus. So complete dissolution will be like this. But you can see that this is not balanced. Why? Because this side I've got how many ions, how many atoms of hydrogen? I've got 2 atoms of hydrogen, and then plus 2. These ones will be equal to 4. And then this side for hydrogen, I've got only what? 3 atoms there. So I need to balance this equation. So this side I can actually get to multiply by 2, and then I would be having 6. So if I multiply by 2 this side, I'll need to multiply by 2 this side. So it would actually be not wise. So it would be easier if I can actually get to go to what? To water directly. So I can actually get to multiply by 2 there. So that at the end of the day, the final reaction would look like this, which is a balanced equation. It will actually look like these are your sulfate ions plus your what? Your 2H3O plus ions. So this is the reaction of your dissolution of sulfuric acid. So that is what we're just supposed to write, guys. You need to know the dissolution of your common acids, especially your nitric acid, and then you go to your what? You go to your sulfuric acid, and then thereafter you go to your hydrochloric acid. So we know that only strong bases, only strong acids as well as strong bases completely ionizes in water. So they are the only ones which completely what dissociates in water. So you need to know those reaction of what of strong bases and what strong acids in water. Now they're saying describe the term acid base indicator. So an acid base indicator, it's a substance that can either have two colors in the presence of what of H plus or OH minus. So you can actually get to say that when it comes to an acid base indicator, you get to say that it is either a weak acid or else a weak base. It is either, you can actually say that it is a weak acid or weak base. Weak acid or weak base, which does what? Which changes color in the presence of either H plus ions or else OH minus ions. Which changes color in the presence of H plus ions or what? OH minus ions. Like for example, you have got your bromomethyl blue, and then you have got your litmus papers. Those are the examples of what? Of acid base indicators. Why do we use those? Because they are able to actually get to change color when they are in the presence of this. That represents, if it changes color in the presence of H plus ions, it actually indicates that the solution is what? Is acidic. If it actually changes color in the presence of OH minus, it shows that the solution is basic. So we need a weak acid or a weak base that is able to change color in the presence of these two. That is what we call an acid base indicator. Now allow me to just get to wrap that. I'm sure we took notes of that. So after saying that, let's go to the following question. So our following question was saying 0.365 grams of hydrogen chloride dissolve in 500 cubic centimeters water at 25 degrees Celsius. This is the reaction. Now they're saying define the term concentration. What is concentration? We know that concentration is equal to the number of moles of solid divided by the molar volume, or else by the volume of the solution. So you can say concentration is the amount of solute in moles dissolved in a unit volume. In a unit volume. In a unit volume of 1 decimeter cubed, or else in a unit volume that is measured in decimeter cubed. That is what we define our concentration as. The amount, the total amount of solute which is in moles dissolved in a unit volume of 1 decimeter cubed. So the units for our concentration there would be moles per decimeter cubed. So you would say that the total amount of solute in moles dissolved in a unit volume of 1 decimeter cubed measured in moles per decimeter cubed. Now they're saying 3.72, calculate the concentration of HCl. How do we calculate that concentration? The concentration of HCl, we are given the mass of that HCl and the volume. So how do we end up here? So what we need to do is to use the mass that we are given to calculate the number of moles of HCl, which will be just mass over molar mass of that HCl. So we can see that the mass is 0.365 grams divided by the molar mass. The atomic mass of hydrogen is 1 plus the atomic mass for chlorine is 35.5. So this is 0.365 divided by 36.5. This is in grams, this is in grams per mole. So that our answer would be in moles. Our answer would be in moles. So if you say 0.365 divided by 36.5, you are going to get what? 0.01. You are going to get 0.01 moles. So these are the number of moles of hydrochloric acid or else hydrogen chloride. And then the concentration now goes to be the number of moles divided by the given volume. So the number of moles, it's 0.01 mole. The given volume, it's in cubic centimeters. We divide by 1000. That I would actually get to come and say 500 divided by 1000. So this one has to be in decimeter cubed. So when you divide by 1000, you are changing cubic centimeters to a decimeter cubed. So this was going to give you a value of, or else you were going supposed to get 0.01 divided by 0.5 in moles per decimeter cubed. And this is actually to a value of what? 0.02 moles per decimeter cubed. That is the concentration of your HCl. Now they are saying calculate the concentration of H3O plus. We use the mole ratio of this as to that. You can see that 1 mole of HCl reacts to form 1 mole of H3O plus. So the number of moles of H3O plus are equivalent to the number of moles of HCl that reacted. Now the volume is the same because they are all dissolved in the same amount of liquid. So now the concentration of H3 plus, you would come and say concentration of H3O plus would be equal to the number of moles of H3O plus divided by the volume. So here it will be the same number of moles that we have here because their molar ratio is just what? 1:1. So this one will be 0.01 moles divided by 0.5 decimeter cubed. And this was going to give you what? It was going to give you the same what? It was going to give you the same concentration, which is 0.02 moles per decimeter cubed. So here they're just examining you if you know how to calculate the concentration of the given product from the balanced equation. So that is how you are going to do it. Now let's go to our next slide. So we now have got question number 4. And question number 4 is saying a major textile dye manufacturer developed a new yellow dye, and the dye has a percent composition of 75.95% carbon, 17.72% nitrogen, 6.3% hydrogen by mass, with a molar mass of 240 grams per mole. Now define the term empirical formula. Empirical formula. So the empirical formula is simply the simplest whole number ratio that you can actually get to find of atoms in a compound. Is the simplest whole number ratio of atoms in a compound, or else in a substance, in a compound. And then determine the empirical formula of this compound. I usually advise that let's use a table. A table makes our life easier for our calculation of our what? Of our empirical formula. A table that you are going to use is actually to say, I need to know my compound that I'm dealing with. And then after knowing my compound, I need to determine the elements that are within my compound. And then I need to determine the mass of each element within that compound. After that, I need to determine the number of moles for each element within that compound. And then after determining the number of moles, I need to determine the simplest ratio of those number of moles within that compound. So here I would be having my what? My elements. So that would be for elements. So you need to list down the your elements within your compound. So within my compound, they say there is carbon, they say there is nitrogen, they say there is hydrogen. And then my compound is given in percentage. So I can take a basis which is just assume a certain mass of my compound to be equal to 100 grams. So that 1% will be equivalent to 1 gram. Now let's look at our mass composition. Let's look at our mass composition. They said 75.9% carbon, 17.72% nitrogen, and 6.33% of hydrogen. These are the same that I'm going to take for my mass. So let's take note of them. So we know that they are saying for carbon, if I can actually get to put them here, is equal to 75.95. For hydrogen, it's equal to 6.33. For nitrogen, it's equal to 17.72. So I'll use this composition here. So I would come and say, I need to know the mass of each, the mass composition of each. This is actually 75.95 grams. And then this one is actually 17.72 grams. And this is actually 6.33 grams. How do I calculate the number of moles of each? I say mass divided by the molar mass. So the number of moles of carbon would simply be equal to 75.95 divided by, let me look into the what? Into the atomic mass of carbon, that is 12. If I divide 75.95, what is the value that I get? If you say 75.95 divided by 12, I get 6.329. 6.329. So this is 6.329, 6.329. And then here, the number of moles of nitrogen would be equal to, if I say 17.72 divided by the atomic mass of nitrogen, which is 14, this is going to be equal to 1.26, 1.266. And then the number of moles of hydrogen will be equal to 6.33 divided by 1. That is the atomic mass of hydrogen. This is also 6.33. Now I need to find my simplest whole number ratio. Simplest whole number ratio. How do I find that? I actually get to determine this smallest value within the number of moles, which is 1.266, and then I divide throughout by that smallest number, so that I get to approximate the whole number that I'm going to get out of that division. So I'll get, say, 6.329 divided by the smallest number of moles, 1.66. This was going to give you what? A value of what? It was going to give you a value of 5. That is the whole number that you get here. Also here, if you say 1.266 divided by 1.266, you are going to get what? 1. And then here, 6.33 divided by 1.266, you are going to get a whole number of 5. So this is the simplest ratio that you are going to find out of your compound. So your compound can actually be what? CHN, like that. It can actually be CHN, because we know that our carbon usually bonds with what? With hydrogen, and then it will later bond with nitrogen. So you now need to actually get to write down this in terms of its simplest ratio. So let me just move it up and show you what I'm saying. We now know the simplest ratio there. I need to have 5 of my what? Of my carbons. I need to have 5 of my carbons. So after having 5 of my carbons, I'll also need to have 5 of my hydrogen. And then I'll need 1 of my what? Of my nitrogen. So the empirical formula was just going to be C5H5 and nitrogen, like that. At some point in time, you need to know how you arrange these atoms in a compound, given that you know a compound. So usually it's in a form of saying carbon, hydrogen, and another atom. Usually it's carbon, hydrogen, another atom. Now let's go to the above question and get to see what they wanted us to find there. Now they're saying determine the molecular formula of this compound. So how do I determine the molecular formula from the information that I have now? So from the information that I have, I will rub this, I would rub this table so that I can use this space, because we now know our empirical formula and we now know how to get that empirical formula. So I would come here and say that our simplest ratio, our simplest whole number ratio was C5H5N. But now I was given the molecular formula of this compound. So this compound is more like X times C5H5N, like that. And its molecular formula is 240 grams per mole. So what we are looking to find is just this end, the X. So I can now first find the molecular mass of what? Of C5H5N. And then I can actually get to divide the total molecular mass of the compound by the molecular mass of this simplest whole number ratio that I have. Then I can find my X. Then I can find my X. That is what I'm looking for there. So I need to find the molecular mass of the simplest whole number ratio. That was going to be equal to 5 times 12, 5 times 12, plus 5 times 1, 5 times 1. So 12 is the atomic mass of carbon, 1 is the atomic mass of hydrogen, and then I'll come and say 1 times 14. This is the atomic mass of nitrogen. This was going to be equal to, it was going to be equal to, this was going to be equal to 79. Now I would actually get to say that X is equal to the total molecular mass that I have for my compound divided by the molecular mass of my simplest whole number ratio, which was going to be equal to 240 grams per each mole, divided by what? Divided by 79 grams per each mole of that simplest ratio. And this was going to give you what? It was going to give you 3. So after finding 3, for me to find my molecular formula of this compound, I'll just come and say molecular formula is equal to 3 times my simplest what? Whole number ratio. By doing that, I would find my molecular formula is 3 times 5, it becomes 15. And then I would have hydrogen there, not nitrogen. And then 3 times 5 is 15 as well. 3 times 1 is just what? 3. So that would be my molecular formula of my what? Of my compound. Now let's go to question number 5. Question number 5 is now saying sodium burns in oxygen according to the following reaction. This sodium, it burns in oxygen to form sodium oxide. And they're saying 483 grams of sodium placed in a container with 5.8 more oxygen gas. Define the term limiting reactant or else limiting reagent. You know that the limiting reagent is that reagent which is actually going to be finished up first, or else that is going to be completely used up first. So you can say that um, a limiting reagent is the chemical reaction, chemical reactant, sorry, chemical reactant that gets used up first in a chemical reaction. In a chemical reaction. So that reactant that gets used up first becomes our what? Our limiting reactant. Or else you would actually get to say a limiting reagent is the chemical reactant that gets used up completely, that gets used up completely in a chemical reaction. So a reactant that will get used up completely in a chemical reaction, it becomes the limiting reagent. Once it's used up, then the reaction stops. That's why we are calling it limiting. Now we are saying determine the limiting reagent in this reaction, which becomes our limiting reagent. How do we determine that? So for us to determine a limiting reagent for that reaction, what we need to do is we need to find the total number of moles of sodium that is present and the total number of moles of oxygen that is present. And then also, in accordance to a balanced reaction, we need to determine the number of moles of sodium that are required by oxygen, as well as the number of oxygen moles that are required by what? By sodium. And then we get to see which one requires less number of moles, or else which one has got less number of moles available for what? For the reaction. So let me just get to show you how we are going to do it. So we are going to calculate the number of moles of sodium present, or else let's get to say what? Available. We are going to calculate the available number of moles of sodium. So that is mass of sodium over. So the mass of the sodium that is available is 483 grams. And then the atomic mass of sodium is what? It's 24. So that will be grams per mole. Now we would actually get to say what becomes the number of moles of sodium there. If you say 283, 483 divided by 24, that becomes what? 21 moles. So we have got 21 moles of sodium available if we are using that given mass. So from this given mass, the amount of sodium that is available is 21 mole. What about the available number of moles of oxygen? The available number of moles of oxygen becomes what? Equal to 5.8 moles, because we are given the number of moles of oxygen that are available there. Then we now need to determine the required number of moles. How much number of moles do we require for sodium? So oxygen requires what? One oxygen requires four sodium, and one oxygen required 4 sodium moles. So we are saying that one requires 4 of sodium. So if my number of oxygen available requires 4 of my sodium, I would actually get to say that 5.8 moles will require 4 times that 5.8, which is equal to what? If you say 4 times 5.8, 4 times 5.8, it will require 23.2 moles. So you can see that oxygen requires 23.2 moles of what? Of sodium. But sodium only has 21 moles of the what? Of the available reactant. So we only have got 21 when we require 23.2. So you can see that at some point in time, our sodium is actually insufficient. It's going to be used up before our oxygen is what? It's used up. So our sodium is going to be what? Our limiting reactant. So here you are going to say that therefore 23.2 moles of sodium is greater than 21 moles of sodium available. Or else I was just supposed to, let me just write it in a way everything is correct there. This one we are saying this one it's got 5.8 more. It requires 4 times 5.8 more of that sodium, so it will require 23.2 more. So you will say required sodium is equal to 23.2 more. And then you get to say 23.2 more of sodium is greater than what? 21 more available. So this is greater than the one that is available. Therefore, sodium is our limiting reagent because it's not enough for oxygen. We only have got lesser what number of moles there. So that is how you would have answered that question. To actually get to say that you first calculate the available number of moles of what? Of your nitrogen, the available number of moles of your oxygen, and then you get to compare using that balanced equation to say how much of sodium is required by oxygen and how much of oxygen is required by sodium. By just calculating the amount of sodium required by oxygen, you can see that sodium is insufficient from what is required by oxygen. So this is going to actually be completely used up. So sodium becomes our limiting reactant. Now let's go to calculate the mass of sodium oxide that can be produced. How do we do that? Let me just get to maybe answer it below here so that I can determine or calculate the mass of sodium oxide that can be produced. So for 5.13, I would come and say that mass is equal to number of moles times what? Molar mass. Do I have the number of moles of sodium oxide that can be produced? Now I need to use my what? I need to use my molar ratio. So sodium oxide, we now get to compare our information with our limiting reactant. So our limiting reactant here, we said it's sodium. So we compare the number of moles of sodium as to the number of moles of what? Of the produced sodium oxide. So we require 4 moles to produce 2. So it's more like we require 2 times the one that we are going to produce. So the amount of sodium oxide that is going to be produced is going to be half of the number of moles of sodium. So half of the number of moles of sodium is half of 21. So now let's actually get to work it out. So the number of moles of sodium oxide there was going to be half of our what? Of our sodium number of moles, which is 21. And then we multiply by the molar mass of what? We want the molar mass of sodium oxide. It's like that. So we would actually get to say 2 times 24 plus 16. So it's more like half of 21 times that. So our mass of sodium oxide that is going to be produced was going to be what? If I say here, this is 10.5 times. So 10.5, I'm multiplying 10.5 with what? I'm multiplying 10.5 with 62. Because this one becomes what? This one becomes 48 plus 16 becomes 62. So if you say 10.5 times 62, you are supposed to get, if I use my calculator, I'm getting 651 grams. So the mass of sodium oxide produced was going to be 651 grams. That is the mass that we are supposed to calculate. Now they are saying calculate the volume of oxygen reacted at STP. Now we actually come back and say that at STP now, we know the amount of volume that is going to be produced, or else the amount of volume covered by each 1 mole of gas. So we are saying that now, since this is the number of moles of sodium that are going to react, how much of the amount of oxygen reacted? This is where we use that same what? That relationship that we were using here. So let me just decongest my workplace here. So at some point in time, you can actually get to see that our oxygen requires 4 times of the sodium. So the number of moles of oxygen that are going to react are going to be equal to what? Are going to be 1/4 of the total of what? Of sodium. So if you come here, you say that the number of moles of oxygen that reacted were going to be equal to 1 over 4 of what? Of the number of moles of sodium, because our sodium is our limiting reactant. So it was going to be equal to 1 over 4 of what? 1 over 4 of 21. 1 over 4 of 21 becomes what? 1 over 4 of 21 uh, becomes equal to what? 1 over 4 of 21 becomes equal to 5.25 moles. So the amount of oxygen that reacted was 4.25 moles. And then now, knowing the amount of oxygen that reacted, we want the volume of oxygen at STP. At what? At STP. We know that at STP, 1 mole of gas occupies 22.4 decimeter cubed. So we just need to multiply the number of moles that we have with what? With the 22.4. So we would come and say 5.25 moles times 22.4 decimeter cubed. That gives us the amount of volume of oxygen that what? That reacted. The amount of oxygen that reacted. So for you to find that amount of oxygen that reacted, you were just going to say that 5.25 times 22.4, this was going to give you a volume of it was supposed to be a volume of 117.6 decimeter cubed, like that. That was the volume of what? Of oxygen at what? At STP that reacted. That was for 5.14. That is what you were just supposed to do there. Consider the balanced chemical equation of magnesium hydroxide with phosphoric acid. Now, this is now a different question. Let's get to see that different question, what it is saying. So I'll shift this on top. I'll shift that on top. Now, let's rub below here so that at least now consider the balanced chemical equation of magnesium hydroxide with phosphoric acid. 3 magnesium hydroxide plus phosphoric acid. So you need 3 moles to react with 2 moles to form 1 mole and 6 moles of what? Calculate the mass of magnesium phosphorate that will be formed assuming 100% yield from the reaction of 15 grams of 92.5% of magnesium hydroxide. So 92.5% of magnesium hydroxide from this. So we are going to say that 92.5% of the theoretical value is the number of moles of magnesium hydroxide that is going to react. And we want the number of moles of this. So we would actually get to relate those number of moles using the mole ratio. What am I saying? Someone would ask, but say, what are you trying to say here? I'm saying that 3 moles of what? 3 moles of magnesium hydroxide reacts to form 1 mole of what? Of magnesium what? Phosphorate. If that is the case, if I know the number of moles of magnesium hydroxide that reacted, if I know the number of moles of magnesium hydroxide that reacted, I can actually get to know the number of moles of magnesium phosphorate that was what? That was produced. So I need to find the theoretical value according to this equation. So I would actually get to say that, okay, fine. I will need to find, let me get to say that, let's read this statement together. They said that calculate the mass of this that will be formed assuming 100% yield. We'll look at this later. From the reaction of what? 15 grams of 92.5%. So we need to find the number of moles of what? Of magnesium hydroxide first. That is equal to the mass over the molar mass. Now the molar mass would be for magnesium hydroxide. So you see that the mass is 92.5% of what? Of 15 grams. That is the mass that is reacting. This is theoretical mass. And then the actual mass that is reacting is 92.5%. So we say 92.5% of 15 grams. How do we do that? We just get to say 92, we just get to say 92.5 over 100 times 15 grams. And then we find the mass that reacted. And then we divide by the what? By the molecular mass of this. So what is the atomic mass of what? Of magnesium. What is the atomic mass of magnesium? Let me just get to show you the periodic table there. I do have the periodic table and I know that magnesium is not that common. So let's go to magnesium. Magnesium is what? It's 24. Magnesium is 24. So we take that 24. I think at some point in time I was using 24 for sodium. Correct for me there if I used 24 for sodium. Sodium is 23. Correct for me there. So here we are saying we have got 24, which is for what? Which is for sodium. We have got 24 plus 2 times of what? 2 times of oxygen is 16 plus 1. This becomes 17. 2 times of 17. So if you do that, what would be the mass? What would be the number of moles that you're going to find? Because this one will be grams per mole. The number of moles that we are going to find there were supposed to be equal to 0.2392. 0.2392. So the total number of moles that we are going to find for magnesium hydroxide were just going to be equal to what? 0.232 moles. Now, if these are the number of moles that are reacting here, how much product is being produced for this one? So you will see that I need I would produce 1/3 of what is reacting here. So you can see that the number of moles of the magnesium phosphorate produced will be equal to the what? It will be simply equal to 1/3 of the number of moles of what? Of magnesium hydroxide, which is 1/3 of 0.392. And this was supposed to be equal to what? This was supposed to be equal to 0.07973 moles. So this is the number of moles of what? Magnesium phosphorate that is produced. But here they said calculate the mass. So you would see that theoretical mass and actual mass are going to be the same because they said 100% yield. But however, let me take it stage by stage and then you see what I'm just trying to say there. So let's just get to first calculate theoretical mass. Theoretical is what we get from calculations. So theoretical mass is what we get from the relationship of this number of moles from the reaction. So we would get to say theoretical mass is equal to number of moles times the molar mass, because we know that number of moles is equal to mass over molar mass. So if I want this, I will just get to cross multiply by that. So the number of moles would be 0.07973 times the molar mass of this. We said the molar mass of that was equal to what? What was the total molar mass of magnesium? What? The total molar mass of what? They want the total molar mass of what here? Just pardon me there. They want the total molar mass of magnesium phosphate. So the total molar mass of magnesium phosphate, we said it's equal to what? To 262 grams per mole. Now, if I multiply that, I should actually be able to find what? I should actually be able to find 20.8892 grams. So this is my theoretical mass. So this is my theoretical mass of magnesium phosphate. But I know that percentage yield is given by actual mass produced all over theoretical mass times 100%. So if my yield is 100% And this side I've got an actual mass, and my theoretical mass here it's 20.8892 grams, and this side times 100. What would be my actual mass? I would simply divide throughout by 100, and this one they'll cancel out. This side I'll be left with 1, and then I'll multiply this by that 1. So you would find out that my actual mass was going to be, this is where I'm saying it was just going to be the same. So my actual mass here, I was going to get actual mass. I was just going to get what? 20.8892 grams. If I take this one, that other side. So that was my actual mass of what? Of my magnesium phosphate that I would have what? Produced. Now let's go to the following question. This was the last question for question number 5. Let's go to question number 6. And question number 6 is our last question for this question paper. And then the question is saying, consider the reaction between sulfur dioxide and oxygen to produce sulfur trioxide. 4 grams of sulfur trioxide is produced at STP. Now they're saying this is the equation. And then they say state Avogadro's law in words. What does Avogadro's law in words say? Avogadro's law, it says that 1 mole of any gas will be equivalent to 6.022 times 10 power 23 what? Number of what? Of entities. Or else you can say 1 mole of gas occupies the same volume at the same temperature and pressure. Because you always know that 1 mole of gas is equal to 6.022 times 10 power 23 particles. And these particles occupy the same volume at what? At standard temperature and pressure. Meaning to say that if you are given standard temperature and what? And pressure, or else at the same temperature and pressure, you would be having the same number of what? Of particles. And those same number of particles will occupy the same volume. So what you would have said in words, you would have just came here and said, let me just get to try to create space so that I can be able to write it neatly there. Uh, Avogadro's law states that 1 mole of any gas at the same temperature and pressure, they occupy the same volume. They occupy the same what? The same volume. 1 mole of any gas at the same temperature and pressure occupy the same volume. Or else 1 mole of any gas at the same temperature and pressure, they will have, or else let's just get to say 1 mole of any gas is equivalent to the same number of particles or entities. But I'm sure this one would be easier and more simpler to say 1 mole of any gas at the same temperature and pressure occupy the same volume. Now, let's say calculate the number of moles of sulfur trioxide. Number of moles is equal to what? To mass divided by the molar mass. Because here we are given a mass of 4 grams. They said 4 grams of sulfur trioxide is produced at STP. So they said number of moles of sulfur trioxide. So 4 grams divided by what? What is the molar mass of what? Of sulfur trioxide. For sulfur, the atomic mass is what? It's 32. And then for oxygen, it's 16 times 3. And then this goes to say this one is gram per mole. The number of moles will be 4 grams divided by that val that you're going to get here. And then the number of moles that you're supposed to find here, you are supposed to find what? 0.05. 0.05 moles. So these are the number of moles of what? Of sulfur trioxide. So these are the number of moles of sulfur trioxide. But the question is saying what? Oh, the question said the number of moles of sulfur dioxide. Now, okay, fine. Let's now determine the number of moles of sulfur dioxide. We have the number of moles of sulfur trioxide. We want the number of moles of sulfur dioxide. The relationship between sulfur trioxide and sulfur dioxide is what? We have 2 moles of sulfur dioxide reacting to form 2 moles of sulfur trioxide. So the number of moles of sulfur trioxide produced are the same number of moles of sulfur dioxide used. So you can see that these ones, they are the same. It's 1:1 or else 2:2. So the number of moles of sulfur dioxide will just be equal to what? 0.05 moles. That will be the number of moles. So they are the same. Now they are saying the volume of sulfur dioxide required in the reaction. So now you know that at STP, 1 mole of gas occupies 22.4. What about if you have got 0.5 moles? So you would come here. This was what? This was supposed to be equal to what? 6.21. Now, what about 6.22? The volume occupied by sulfur trioxide or else required, you would know that it would be 0.05 moles times 22.4 decimeter cubed for every mole of any gas. So that here, these ones, they will cancel out. And then your volume of the sulfur trioxide there that you're going to find was going to be equal to 1.12 decimeter cubed. So the volume of sulfur dioxide that was required was equal to 1.12 decimeter cubed. And then what about the mass of oxygen that has been used up? Let's look at the reaction again and let's try to find the relationship of oxygen and sulfur trioxide. Let me just get to wrap things here. The relationship between oxygen and sulfur trioxide is what? What is the mole ratio there? What is the mole ratio there in between those two? You can see that 1 mole of oxygen is going to produce what? 2 moles of what? Sulfur trioxide. So the relationship is 1:1. So if I know the number of what? Of sulfur trioxide, I can know the number of moles of what? Of oxygen. Where I'm saying the relationship here is what? It's 2:1. So if I know the number of moles of sulfur trioxide, which is 0.05 mole, then I can know the number of oxygen. So now I would know that the number of oxygen definitely would be equal to what? Half of the 0.05. Because if I take this x that side, I'll take 2 down and 1 on top. That will be 1/2 times that. So it will be equal to what? Half of 0.05 moles becomes 0.0 what? 0.025. This one becomes 0.025 moles. And then for us to find the mass, we now need to say mass is equal to number of moles times the molar mass or the atomic mass of oxygen. So the atomic mass of oxygen is 32. So that would be 0.025 times 32. And then the mass there would simply be equal to 0.025 times 32. What becomes the value there? So I'm simply saying that here it was 0.025 times 32 grams per each mole. So this one was going to be equal to what? It was going to be equivalent to 0.8 grams. So that was the mass of what? Of our oxygen gas. Write down a combustion reaction of C4H10 with excess oxygen. So with excess oxygen, there is going to be what we refer to as what? Complete combustion. Complete combustion. So complete combustion would be C4H10 plus our excess oxygen to form CXH. We're actually going to form what? See now what I'm doing. We are supposed to form carbon dioxide and water. Those are the two products of what? Of complete combustion. Wherever there is complete combustion, just know that you are going to produce what? Carbon dioxide and water. Those are the two products. So we know that just like for neutralization reaction, we need to know the what? The products. Same as for complete combustion. So for complete combustion, the reaction has to produce what? We are saying C4H10 reacting with excess oxygen to form carbon dioxide plus what? Now we now need to balance. How many number of what? Carbon atoms that do I have on my left hand side? I have got 4 for carbon. This side I've got 1. So I need to multiply by 4 there. After multiplying by 4, I also come to hydrogen. I have got 10. This side I've got what? I've got 2. So I can multiply by 5 there. But you can see that now for oxygen, this side I now have got 8 here plus my 5 this side, they become 13. This side I need 13. So I can come and say 13 divided by 2. So that this would actually be 2 times 2. Then I can remain with 13 this side. So this would be the complete what? Combustion reaction. So what you need to know is how your reaction of what? Of hydrocarbons is with excess oxygen. It's complete combustion. And then after complete combustion, you need to actually get to what? To balance this reaction. At some point in time, since they said that just write down the combustion reaction, they didn't say what? Balance. They didn't say balance. So you can actually get to say what? You can actually get to come and say C4H10 plus oxygen to actually get to form what? Carbon dioxide plus water. So if they do not say balanced, you can even write this. You know that when it reacts with oxygen, it has to form carbon dioxide and water. So, guys, this was our question paper from OR Tambo district, which was for September 2023. Let's continue to revise, guys. We actually wish for you to win. We actually get to say more light and continue shining and shining. So let's meet once again in our next coming videos on our physical sciences revision. So I would actually get to say for today, thank you for being here together with me. Let's meet in our next coming videos.